Hi learners, welcome back to Dilk. So before starting this session, if you have not watched the previous videos on the basicity of amines, especially the discussion on Kb, pKb, alkyl amines versus ammonia and the effect of solvation, steric hindrance, I strongly recommend watching those videos first because this session is a continuation of the same topic. So in today's video, which is the final part of the basicity of amines discussion, we are going to understand one of the most important concept in aromatic amines. Why aryl amines like aniline are less basic than ammonia and alkyl amines. So we will mainly focus on the role of resonance and how the lone pairs present on the nitrogen behaves differently in aniline compared to aliphatic amines. So we will also discuss how different substituents attached to the benzene ring can increase or decrease the basicity of aniline. So let us begin with the comparison between aryl amines and ammonia. Here we are talking aniline as the example of an aryl amine. In aniline, what is aniline? Aniline is to a benzene ring and NH2 group is attached. So in aniline, the nitrogen atom contains a lone pair of electron just like in ammonia. But the important difference is that in aniline, the nitrogen atom is directly attached to a benzene ring. In ammonia, nitrogen atom is attached to 3 hydrogen atoms, but in aniline, nitrogen atom is attached to 2 hydrogen atoms and 1 benzene ring. Now let us carefully understand what happens. The lone pair present on nitrogen does not remain completely localized on nitrogen. It is delocalized. We will discuss this term, localized and delocalized. In nitrogen NH3 ammonia, what is happening? This lone pair which present on this nitrogen atom, it is localized. It is not moving anywhere. But in case of aniline, this lone pairs, it is moving around the benzene ring. Means it is delocalized. It is not localized at nitrogen atom. It is delocalized throughout the benzene ring. In the first structure, look at this. The lone pair is present on nitrogen atom. Then the lone pair moves towards benzene ring and forms a double bond between nitrogen and the carbon attached to it. So this is the first structure of aniline. Then this lone pair on nitrogen atom is shifted to the benzene ring. So as a result of that, a carbon-carbon bond is shifted to the ortho position and a carbon-nitrogen double bond is formed, and due to the donation of electrons, nitrogen atom will get a positive charge. So because of this movement of electrons, a negative charge appears at the ortho position of the ring. In the second structure, the negative charge is present at the ortho position of the ring, while nitrogen acquires a positive charge because it has donated its lone pairs to the ring, right? So now the electrons continue to move within the ring, shifting the negative charge to the para position, then again to the ortho position, and it will go back to the nitrogen atom. So in the first structure, it is the simple aniline. Next, electrons to the benzene ring. So we got the second structure and the negative charge is at the ortho position. Then again the negative charge is shifting. Then it is at the para position. Then again it will shift and it is present in the ortho position. It will go back to the nitrogen and we will get the resonance structure. So there are totally 5 resonance structures. So because of resonance, the lone pair originally present on nitrogen becomes distributed over the benzene ring instead of remaining fully available on nitrogen. So this is the most important point. Since the lone pair is delocalized into the aromatic ring, it becomes less available for protonation. Therefore, aniline cannot accept a proton as easily as ammonia or alkyl amines. In ammonia and alkyl amines, the lone pair on the nitrogen atom is localized, but in aniline, the nitrogen lone pair is delocalized toward the ring, so it becomes less available for protonation. So therefore, we can say aniline cannot accept a proton as easily as ammonia or alkyl amines. Now, let us compare this with the anilinium ions, which is formed after protonation. So after protonation, aniline on protonation, we will get anilinium ion. So how many resonance structures are possible for anilinium ion? There are only 2 resonance structures possible. Okay, the first one and the second one. So anilinium ion has fewer resonance structures and is less resonance stabilized compared to aniline itself. So why it has only 2 structures? Because when aniline accepts a proton, the nitrogen becomes positively charged. You can see the positive charge on the nitrogen atom. And the lone pair is no longer available for resonance. Because of this, the conjugated acid, that is a anilinium ion, has fewer resonance structures and is less resonance stabilized compared to aniline itself. So aniline remains more stable in the unprotonated form due to resonance stabilization. Since protonation destroys this resonance stabilization, aniline shows lower tendency to accept a proton. Therefore, aniline behaves as a weaker basis than ammonia. Because of these two reasons, we can say aryl amines are less basic compared to ammonia and aliphatic amines. Alkyl amines are stronger bases than ammonia because of the plus I effects, while aryl amines like aniline are weaker bases because the lone pairs gets delocalized into the benzene ring through the resonance. Now let us move to the next part where we will discuss the substituent effect on aniline. So before moving to that, we can finalize lone pairs on nitrogen is conjugation with the ring, less available for protonation. Then aniline, which has 5 resonance structures, is more stable than anilinium ion, which has only 2 resonance structures. So rather than accepting the proton and undergoing to the anilinium ion formation, the conjugate acid formation, it prefers the aniline structure itself. So we can say lower proton acceptability. So aniline is a weaker base than ammonia. Now we can discuss if substituents are present in aniline, what will be the effect of basicity. So the basicity of aniline can further change depending on the groups attached to the benzene ring. These groups can either increase or decrease electron density around the nitrogen atom. So according to that, the basicity can change. First, let us discuss electron donating groups such as methoxy and methyl or ethyl groups. These type of groups, they will donate electron density into the benzene ring. They have plus I effects, right? So they will donate electron density to the benzene ring. So they will increase the electron density in the benzene ring. So this increases the electron density around the nitrogen atom and makes the lone pair more available for protonation. Therefore, electron donating groups increase the basicity of aniline. So what is the reason? These groups push electron density into the ring and onto the nitrogen atom, and therefore the lone pair is more available for protonation compared to simple anilines or simple aryl amines. But if the substituents are electron-withdrawing groups means they will withdraw electrons towards them. For example, nitro NO2 or sulfonic group SO3H or carboxyl groups such as COOH or halogen atoms such as bromine, iodine or chlorine. What will happen? They will pull electron density away from the benzene ring. They will pull electron density towards them, and therefore the electron density becomes away from the benzene ring and nitrogen atom. As a result, the lone pair on nitrogen becomes less available for protonation. Therefore, we can say electron withdrawing groups decrease the basicity of aniline. So what is the reason? These groups pull electron density away from nitrogen. The lone pair is less available for protonation, so they are less basic than aniline. We can say basicity of aromatic amines depends not only on the resonance but also on the nature of substituents attached to the ring. Electron donating groups will increase basicity while electron withdrawing group will decrease the basicity. So learners, with this we have completed the complete discussion on the basicity of amines, including why amines are basic, the Kb and pKb values, alkyl amine versus ammonia, effect of solvation, the steric hindrances, and aryl amines versus ammonia, resonance effect in aniline, substituent effects in aromatic amines. So I hope this series you clearly understand the logic behind the basicity of amines instead of just memorizing the orders. So we can just wind up the points here. The order of basicity in gas phase, it is tertiary, then secondary amines, then primary amines, then ammonia. So what is in aliphatic versus ammonia? We have discussed that due to the plus effect of alkyl groups, electron density increase on nitrogen atoms, so they are more basic. And alkyl amines are stronger bases than ammonia. Then aqueous phase order varies due to solvation, right? And smaller ions, more solvation, more stability. And we have the order for ethyl amines and methyl amines. In case of methyl amines, secondary, then primary, then tertiary, then ammonia. In ethyl amines, secondary, then tertiary, then primary amines. So in both cases, secondary amines are more basic. In aryl amines versus ammonia, NH2 conjugated with the benzene ring, lone pair is delocalized into the ring, So 5 resonance structures is possible for anilines. Only 2 resonance structures in anilinium ion, which is a conjugate acid. Therefore, aniline is more stable than its ion. So aryl amines are less basic than ammonia. So we can say aromatic amines are weaker bases than ammonia. Then the final point, the electron donating group will increase the basicity while electron withdrawing group will decrease the basicity. So I hope all these concepts are clear for you. So keep practicing and keep learning, and I will see you in the next topic.